Ntfs is a proprietary file system developed by Microsoft. Starting with Windows NT 3.1, it is the default file system of Windows NT family. Ntfs has several technical improvements over FAT and HPFS, the file systems that it superseded, such as improved support for metadata, and the use of advanced data structures to improve performance, reliability, and disk space utilization, plus additional extensions such as security access control lists and file system journaling. History. In the mid-1980s, Microsoft and IBM formed a joint project to create the next generation of graphical operating system. The result of the project was OS/2, but Microsoft and IBM disagreed on many important issues and eventually separated. OS/2 remained an IBM project and Microsoft worked on Windows NT. The OS/2 file system HPFS contained several important new features. When Microsoft created their new operating system, they borrowed many of these concepts for Ntfs. Probably as a result of this common ancestry, HPFS and Ntfs use the same disk partition identification type code. Using the same partition ID record number is unusual, since there were dozens of available codes, and other major file systems have their own code. FAT has more than 9 algorithms identifying the file system in a partition type 07 must perform additional checks. Developers. Ntfs developers include Tom Miller, Gary Kimura, Brian Andrew, David Goebel. Versions. Microsoft has released 5 versions of Ntfs. v1.0, released with Windows NT 3.1 in 1993. v1.0 is incompatible with v1.1 and newer volumes written by Windows NT 3.5x cannot be read by Windows NT 3.1 until an update is installed. v1.2, released with Windows NT 3.51 in 1995, supports compressed files, named streams and access control lists. v3.0, released with Windows 2000, supports disk quotas, encrypting file system, sparse files, reparse points, update sequence number journaling, the $extend folder and its files. Reorganized security descriptors so that multiple files using the same security setting can share the same descriptor. v3.1, released with Windows XP in autumn 2001, expanded the master file table entries with redundant MFT record number. The Ntfs.sys version number should not be confused with the Ntfs format version number. Although subsequent versions of Windows added new file system-related features, they did not change Ntfs itself. For example, Windows Vista implemented Ntfs symbolic links, transactional Ntfs, partition shrinking and self-healing. All except Ntfs symbolic links are operating systems features. Ntfs v3.0 includes several new features over its predecessors. Sparse file support, disk usage quotas, reparse points, distributed link tracking, and file-level encryption, also known as the encrypting file system. Scalability. In theory, the maximum Ntfs volume size is 264-1 clusters. However, the maximum Ntfs volume size as implemented in Windows XP Professional is 232-1 clusters, partly due to partition table limitations. For example, using 64 KB clusters, the maximum Windows XP Ntfs volume size is 256 TB -64 KB. Using the default cluster size of 4 KB, the maximum Ntfs volume size is 16 TB -4 KB. Because partition tables on master boot record disks only support partition sizes up to 2 TB, dynamic or GPT volumes must be used to create Ntfs volumes over 2 TB. booting from a GPT volume to a Windows environment in a Microsoft-supported way requires a system with UEFI and 64-bit support. The maximum theoretical file size on Ntfs is 16 UB-1 KB or 1844674407370955059 bytes. With Windows 8 and Windows Server 2012, the maximum file size implemented is 256 terabytes minus 64 kilobytes or 281,474,976,645,120 bytes. Ntfs supports a maximum cluster size of 64 kilobytes. Journaling. Ntfs is a journaling file system and uses the Ntfs log to record metadata changes to the volume. It is a critical functionality of Ntfs for ensuring that its internal complex data structures, or data moves performed by the defragmentation API, the modifications to MFT records, and indices will remain consistent in case of system crashes, and allow easy rollback of uncommitted changes to these critical data structures when the volume is remounted. The Usn Journal is a system management feature that records changes to files, streams and directories on the volume, as well as their various attributes and security settings. The journal is made available for applications to track changes to the volume. This journal can be enabled or disabled on non-system volumes. Hard links. Hard links allows different file names to refer to the same file contents. Hard links are similar to directory junctions, but refer to files instead. Hard links may link to files in the same volume only because each volume has its own MFD. Hard links have their own file metadata, so a change in file size or attributes under one hard link may not update the others until they are opened. Hard links were originally included to support the POSIX subsystem in Windows NT. Windows uses hard links to support short file names in Ntfs. Operating system support is needed because there are legacy applications that can work only with 8.3 file names. In this case, an additional file name record and directory entry is added, but both 8.3 and long file name are linked and updated together. Unlike a regular hard link, alternate data streams allow more than one data stream to be associated with a file name, using the format file name, stream name. Ntfs streams were introduced in Windows NT 3.1 to enable services for Macintosh to store resource forks. Although current versions of Windows Server no longer include SFM, third-party Apple filing protocol products still use this feature of the file system. Very small adds are added by Internet Explorer and recently by other browsers to mark files downloaded from external sites as possibly unsafe to run. The local shell would then require user confirmation before opening them. When the user indicates that they no longer want this confirmation dialog, this add is deleted. Alternate streams are not listed in Windows Explorer, and their size is not included in the file's size. They are ignored when the file is copied or moved to another file system without add support, attached to an email, or uploaded to a website. Thus, using alternate streams for critical data may cause problems. Microsoft provides a tool called Streams to view streams on a selected volume. Starting with Windows PowerShell 3.0, it is possible to manage adds natively with 7 cmdlets. Add content, clear content, get item, out string, remove item, set content. Malware has used alternate data streams to hide code. As a result, malware scanners and other special tools now check for alternate data streams. File compression. Ntfs can compress files using LZNT1 algorithm. Files are compressed in 16 cluster chunks. With 4 KB clusters, files are compressed in 64 KB chunks. The compression algorithms in Ntfs are designed to support cluster sizes of up to 4 kilobytes. When the cluster size is greater than 4 kilobytes on an Ntfs volume, Ntfs compression is not available. If the compression reduces 64 kilobytes of data to 60 kilobytes or less, Ntfs treats the unneeded 4 kilobytes pages like empty sparse file clusters. They are not written. This allows for reasonable random access times, as the OS just has to follow the chain of fragments. However, large compressible files become highly fragmented since every chunk less than 64 kilobytes becomes a fragment. Single-user systems with limited hard disk space can benefit from Ntfs compression for small files, from 4 kilobytes to 64 kilobytes or more, depending on compressibility. Files less than 900 bytes or so are stored within the directory entry at the MFD. Flash memory, such as SSD drives, do not have the head movement delays of hard disk drives, so fragmentation has only small effects. Users of fast multi-core processors will find improvements in application speed by compressing their applications and data, as well as a reduction in space used. Note that SSDs with SandForce controllers already compress data. However, since less data is transferred, there is a reduction in IOs. The best use of compression is for files that are repetitive, seldom written, usually accessed sequentially, and not themselves compressed. Log files are an ideal example. Compressing system files needed at boot time, like drivers, ntldr, winload.x, or bootmgr, may prevent the system from booting correctly, as compression filters are not available then. However, in later editions of Windows, compression of important system files is disallowed. Files may be compressed or decompressed individually for a drive, directory, or directory tree, becoming a default for the files inside. Although read-write access to compressed files is mostly transparent, Microsoft recommends avoiding compression on server systems or network shares holding roaming profiles because it puts a considerable load on the processor. Since many fragments are created for compressible files, defragmentation may take longer. Sparse files are files interspersed with empty segments for which no actual storage space is used. To the applications, the file looks like an ordinary file with empty regions seen as regions filled with zeros. Database applications, for instance, may use sparse files. As with compressed files, the actual sizes of sparse files are not taken into account when determining quota limits. Volume shadow copy. The volume shadow copy service keeps historical versions of files and folders on Ntfs volumes by copying old, newly overwritten data to shadow copy via copy-on-write technique. The user may later request an earlier version to be recovered. This also allows data backup programs to archive files currently in use by the file system. On heavily loaded systems, Microsoft recommends setting up a shadow copy volume on a separate disk. Windows Vista also introduced persistent shadow copies for use with System Restore and previous versions features. Persistent shadow copies, however, are deleted when an older operating system mounts that Ntfs volume. This happens because the older operating system does not understand the newer format of persistent shadow copies. Transactions. As of Windows Vista, applications can use transactional Ntfs to group changes to files together into a transaction. The transaction will guarantee that all changes happen, or none of them do, and it will guarantee that applications outside the transaction will not see the changes until they are committed. It uses similar techniques as those used for volume shadow copies to ensure that overwritten data can be safely rolled back, and a CLFS log to mark the transactions that have still not been committed, or those that have been committed but still not fully applied. Transactional Ntfs does not restrict transactions to just the local Ntfs volume. but also includes other transactional data or operations in other locations, such as data stored in separate volumes, the local registry, or SQL databases, or the current states of system services or remote services. These transactions are coordinated network-wide with all participants using a specific service, the DTC, to ensure that all participants will receive same commit state, and to transport the changes that have been validated by any participant. Transactional Ntfs allows, for example, the creation of network-wide consistent distributed file systems, including with their local live or offline caches. Microsoft now advise against using Ntfs. Microsoft strongly recommends developers utilize alternative means, since Ntfs may not be available in future versions of Microsoft Windows. Security in Ntfs. Each file or folder is assigned a security descriptor that defines its owner and contains two access control lists. The first ACL, called Discretionary Access Control List, defines exactly what type of interaction is allowed or forbidden by which user or groups of users. For example, files in C, Program Files folder may be read and executed by all users but only modified by a user holding administrative privileges. Windows Vista adds mandatory access control info to DACLs. DACLs are the primary focus of user account control in Windows Vista and later. The second ACL, called System Access Control List, defines what interactions with the file or folder is to be audited, and whether they should be logged when the activity is successful, failed, or both. For example, auditing can be enabled on sensitive files of a company, so that its managers get to know when someone tries to delete them or make a copy of them, and whether he or she succeeds. Encrypting file system provides strong and user-transparent encryption of any file or folder on an Ntfs volume. EFS works in conjunction with the EFS service, Microsoft's cryptography, and the EFS file system runtime library. EFS works by encrypting a file with a bulk symmetric key, which is used because it takes a relatively small amount of time to encrypt and decrypt large amounts of data than if an asymmetric key cipher is used. The symmetric key that is used to encrypt the file is then encrypted with a public key that is associated with the user who encrypted the file, and this encrypted data is stored in an alternate data stream of the encrypted file. To decrypt the file system uses the private key of the user to decrypt the symmetric key that is stored in the file header. It then uses the symmetric key to decrypt the file. Because this is done at the file system level, it is transparent to the user. Also, in case of a user losing access to their key, support for additional decryption keys has been built into the EFS system, so that a recovery agent can still access the files if needed. Ntfs provided encryption and Ntfs provided compression are mutually exclusive. However, Ntfs can be used for one and a third-party tool for the other. The support of EFS is not available in Basic, Home and Media Center versions of Windows, and must be activated after installation of Professional, Ultimate and Server versions of Windows or by using enterprise deployment tools within Windows domains. Disk quotas were introduced in Ntfs v3. They allow the administrator of a computer that runs a version of Windows that supports Ntfs to set a threshold of disk space that users may use. It also allows administrators to keep track of how much disk space each user is using. An administrator may specify a certain level of disk space that a user may use before they receive a warning, and then deny access to the user once they hit their upper limit of space. Disk quotas do not take into account Ntfs's transparent file compression. Should this be enabled, Applications that query the amount of free space will also see the amount of free space left to the user who has a quota applied to them. Reparse points. Ntfs reparse points, introduced in Ntfs v3, are used by associating a reparse tag in the user space attribute of a file or directory. Microsoft includes several default tags including Ntfs symbolic links, directory junction points and volume mount points. When the Object Manager parses a file system name lookup and encounters a reparse attribute, it will reparse the name lookup, passing the user-controlled reparse data to every file system filter driver that is loaded into Windows. Each filter driver examines the reparse data to see whether it is associated with that reparse point, and if that filter driver determines a match, then it intercepts the file system call and executes its special functionality. Resizing. Starting with Windows Vista, Microsoft added the built-in ability to shrink or expand a partition. But this capability is limited because it will not relocate page file fragments or files that have been marked as unmovable. So shrinking will often require relocating or disabling any page file, the index of Windows search, and any shadow copy used by System Restore. Various third-party tools are capable of resizing Ntfs partitions.